The airspace above the Japanese home islands in the winter of 1944 and 1945 was a hostile alien environment characterized by meteorological extremes that fundamentally altered the physics of aerial warfare. At an altitude of 30,000 feet, the ambient temperature routinely plummeted to 60 degrees below zero Fahrenheit. This was the domain of a newly discovered atmospheric phenomenon known as the jet stream, a violently fast river of high-altitude wind that tore across the Pacific Ocean from west to east at velocities frequently exceeding 150 to 200 miles per hour. For the pilots of the Imperial Japanese Army Air Service and the Imperial Japanese Navy Air Service attempting to defend their homeland against the encroaching American heavy bomber fleets, this environment was a physical and mechanical purgatory. A Japanese pilot strapped into the freezing unpressurized cockpit of a Kawasaki Ki-45 Toryu or a Nakajima Ki-84 Hayate faced insurmountable obstacles before he even engaged the enemy. Japanese aviation metallurgy and engine design, struggling under the suffocating weight of an Allied blockade and severe resource shortages, had largely failed to master the highly complex engineering required for efficient high-altitude two-stage exhaust-driven turbo superchargers. As the Japanese interceptors clawed their way toward the stratosphere, the thin, freezing air choked their radial engines, starving them of oxygen and robbing them of horsepower. Engine oil congealed into a sluggish, gelatinous paste, aircraft control cables contracted and stiffened, and the pilots themselves, heavily layered in bulky electrically heated suits that frequently short-circuited, suffered from debilitating hypoxia and bone-deep cold. Their aircraft, sluggish and operating at the absolute limits of their performance envelopes, were forced to stagger into the skies to confront the ultimate expression of American aeronautical engineering, the Boeing B-29 Superfortress. To understand the profound technological shock the B-29 delivered to the Japanese defenders, one must examine the fundamental architectural shift it represented in strategic bomber design. Prior to the Superfortress, the American Army Air Forces relied on the Boeing B-17 Flying Fortress and the consolidated B-24 Liberator to conduct daylight precision bombing over Europe. While heavily armed, these older bombers forced their crews to endure the same brutal atmospheric conditions as the enemy fighters. Gunners in AB-17 stood in open waist windows or crouched in unheated plexiglass turrets, breathing through freezing oxygen masks while the slipstream blasted them with sub-zero air. In combat, the physical exhaustion of simply surviving at 25,000 feet severely degraded a gunner's situational awareness and marksmanship. The intense vibration of the airframe, the extreme cold numbing the gunner's hands, and the sheer physical effort required to manually crank heavy gun turrets against the immense aerodynamic pressure of the slipstream meant that manned turrets were fundamentally inaccurate. When the United States Army Air Forces issued the requirements for the very heavy bomber project that would become the B-29, they explicitly demanded a pressurized cabin. By sealing the forward cockpit, the central gunner's compartment, and the tail section, and pumping in warm compressed air bled from the superchargers of the massive Wright R3350 duplex Cyclone radial engines, Boeing created an environment where crews could operate at 30,000 feet in standard flight suits without cumbersome oxygen masks. But this pressurization mandate created a massive engineering dilemma regarding the bomber's defensive armament. If the crew compartments were pressurized, they could not be punctured by the open gaps required for traditional manned gun turrets. A manned turret requires a large hole in the fuselage for the gunner to sit in, which would instantly depressurize the aircraft. Furthermore, the aerodynamic drag created by bulky manned turrets protruding from the fuselage would severely compromise the B-29's required top speed of over 350 miles per hour and its extreme operational range of over 3,000 miles. The solution to this complex engineering problem was one of the most closely guarded secrets of the Second World War and the single most terrifying technological advancement encountered by the Japanese interceptor pilots. It was the central fire control system designed and manufactured by the General Electric Company. General Electric engineers entirely discarded the concept of the gunner sitting inside the turret with the guns. Instead, they developed a completely remote-controlled weapons system that fundamentally removed human error and physical exhaustion from the equation of aerial gunnery. The B-29 was equipped with 4 remote-controlled turrets located on the upper forward, upper aft, lower forward, and lower aft sections of the fuselage, plus a manned but isolated tail turret. These turrets housed a total of 12 50 caliber Browning M2 heavy machine guns and initially a 20 mm cannon in the tail. The guns were positioned outside the pressurized hull, housed in low-profile, aerodynamically streamlined aerodynamic domes that drastically reduced drag, while the gunners sat safely inside the warm pressurized cabin, aiming the weapons through heavy blistered windows using advanced optical sighting stations. The sheer mechanical brilliance of the General Electric Central Fire Control System lay in its use of an analog computer network to solve the incredibly complex differential equations of aerial ballistics in real time. In a traditional bomber, a gunner firing at a moving fighter plane had to manually guess the required lead distance, estimating the target's speed, angle, and distance using rudimentary ring and bead sights. At the closing speeds of late war combat, this manual estimation was practically useless. The General Electric system automated this process through a network of electromechanical analog computers housed deep within the fuselage of the B-29. When a Japanese fighter approached the superfortress, the American gunner positioned at one of the 5 sighting stations would locate the target through his optical sight. The gunner would then frame the wingspan of the enemy fighter within a circle of glowing orange dots projected onto his combining glass. Because the wingspans of all known Japanese fighters were pre-calculated and memorized by the gunner, adjusting the size of this glowing circle until it perfectly framed the wingspan automatically fed the exact range of the target into the analog computer. The gunner then simply tracked the target, keeping it centered in the crosshairs. As he smoothly moved, the sighting mechanism and internal gyroscope measured the exact rate of traverse and elevation. This raw data regarding range and angular velocity was immediately transmitted to the analog computers, but the calculations were far from complete. To accurately hit a rapidly moving target from a bomber that was itself traveling at 300 miles per hour through the freezing jet stream, the computer had to factor in a staggering array of physical and meteorological variables. The computer automatically calculated the exact ballistic drop of the .50 caliber projectile due to gravity over the specified distance. It calculated the aerodynamic drag acting on the bullet as it passed through the thin air at 30,000 feet, predicting its deceleration. It accounted for the specific airspeed of the B-29 and the ambient air density, feeding data directly from the bomber's pitot tubes and altimeters. Most importantly, the computer calculated the massive windage effect created by the bomber's own forward velocity, which would dramatically curve the trajectory of a bullet fired sideways from the fuselage. But the most brilliant mathematical achievement of the General Electric analog computer was its automatic calculation of parallax. Because the gunner aiming the sight was located several yards away from the actual turret firing the guns, their lines of sight were fundamentally different. If the guns simply pointed exactly where the gunner was looking, the bullets would miss the target by the exact distance between the gunner and the turret. The analog computer constantly solved this shifting geometric problem, slightly converging the angle of the gun barrels so that the streams of .50 caliber bullets would intersect precisely at the exact point in space where the target was located. The mechanism that translated these complex mathematical solutions into physical movement was a marvel of electrical engineering, utilizing devices known as Selson generators and motors. Selson, which stood for self-synchronous, was a system of electrical transmission that allowed precise rotational movements to be copied remotely. As the analog computer calculated the perfect firing solution, it turned a small internal Selson generator. This generator sent a precise electrical current through miles of wiring running along the pressurized bulkheads of the B-29 to a corresponding Selson motor located inside the base of the remote turret. The motor then activated massive hydraulic amplitude drives that violently but smoothly whipped the heavy gun turrets into position, matching the computer's calculations with an accuracy measured in tiny fractions of a degree. The speed and precision of the amplitude drives were terrifying. A remote turret could traverse a full 360 degrees in less than 3 seconds, swinging the heavy .50 caliber machine guns onto a target faster than any human gunner could physically rotate a mechanical crank. For the Japanese pilot attempting to approach the bomber, this system presented a completely unnatural and insurmountable defensive shield. When a Japanese pilot flying his Mitsubishi A6M0 or Nakajima Ki-44 Shoki managed to struggle up to the operational altitude of the B-29 formations, he encountered a tactical geometry that defied all his previous combat experience. Traditional fighter tactics dictated attacking a bomber from its blind spots, usually the steep overhead pass or the direct frontal assault where the closing speeds minimized the bomber's defensive fire. But the B-29 had no blind spots. The 4 fuselage turrets and the tail stinger provided a fully overlapping 360-degree hemisphere of defensive fire. Furthermore, the central fire control system featured an unprecedented master gunner hierarchy that multiplied the lethality of the turrets. The B-29 possessed 5 sighting stations: the nose gunner, the tail gunner, the left blister gunner, the right blister gunner, and the central fire control master gunner, who sat in a highly elevated ring blister on the top of the fuselage. The master gunner possessed a master control panel that allowed him to instantly distribute control of the 4 main turrets among the various sighting stations. If a Japanese fighter formation attacked from the right side, the master gunner could instantly transfer control of the upper forward, and lower aft turrets to the right blister gunner. This meant that a single American gunner tracking a single Japanese fighter in his optical sight was now simultaneously commanding up to 8 50 caliber heavy machine guns. As the gunner smoothly tracked the target, the analog computers calculated the individual parallax for each separate turret, converging all 8 gun barrels to create an unavoidable cone of synchronized fire. The Japanese pilots, accustomed to dodging the erratic, inaccurate tracer fire of manually operated turrets, suddenly found themselves being tracked by invisible mechanical brains. As they initiated their attack runs, they could literally see the low-profile turrets on the B-29 snapping into position, swiveling with a sudden robotic precision that was completely detached from the movement of the bomber itself. The guns would elevate and track the incoming fighter flawlessly, regardless of the evasive maneuvers the Japanese pilot attempted. When the American gunner depressed the firing triggers on his yoke, the result was a concentrated wall of armor-piercing incendiary ammunition traveling at nearly 3,000 feet per second. The 50 caliber Browning M2 was a devastatingly powerful weapon capable of punching through engine blocks, severing wing spars, and instantly igniting the notoriously unprotected fuel tanks of the Japanese interceptors. The psychological toll this inflicted on the Japanese air defense forces was catastrophic. An elite Japanese interceptor pilot, having expended immense physical effort just to keep his aircraft flying in the freezing, oxygen-starved stratosphere, found himself flying into a mathematically perfect kill zone. If he tried a slashing attack from the side, the analog computers perfectly calculated his lead and the guns tracked him across the sky. If he tried to dive from above, the upper turrets snapped upward and filled his path with high explosive rounds. The central fire control system was so accurate that American gunners were ordered to fire short bursts, not to conserve ammunition but because the computers required the gunner to maintain a smooth, continuous track on the target. If the gunner simply held down the trigger, the vibration of his own aircraft might momentarily disrupt the analog track. By firing in precise, calculated bursts, the gunner allowed the computer to constantly refine the mathematical solution, ensuring that every subsequent burst was more accurate than the last. The Japanese pilots, lacking self-sealing fuel tanks and adequate pilot armor in most of their interceptor models, were systematically shredded by a weapon system they could not outmaneuver, outclimb, or outsmart. The utter frustration of the Japanese high command in the face of this technological disparity led to profound and desperate tactical shifts. Realizing that conventional fighter attacks against the overlapping computerized fire of AB-29 formation were essentially suicidal, the Imperial Japanese Army Air Service began forming dedicated ramming units known as Shinten Seiku Tai, or heaven-shaking air superiority units. These pilots were ordered to strip their aircraft of all heavy weapons armor and radios to maximize their climb rate and high-altitude performance. Their sole objective was to physically crash their aircraft into the massive wings or tail sections of the superfortresses, bypassing the central fire control system entirely by sacrificing themselves. This grim tactic was a direct admission that the Japanese aviation industry and military doctrine possessed no mechanical or technical countermeasure to the General Electric analog computer. While these ramming attacks occasionally succeeded in bringing down AB-29, they represented a horrific expenditure of pilot lives and aircraft that a collapsing industrial nation could ill afford. The fact that the Japanese were forced to resort to guided human missiles to combat a defensive gun turret perfectly illustrates the unbridgeable technological chasm that had opened between the two nations. Even the most advanced Japanese interceptors deployed late in the war, such as the formidable Kyushu J-7W Shinden with its radical canard design or the twin-engine Mitsubishi Ki-83 high-altitude fighter, remained fundamentally limited by their reliance on human marksmanship and mechanical sighting against the computerized defensive grid of the American bombers. The B-29's central fire control system had effectively automated the defense of the bomber, shifting the burden of survival from the physical endurance of the crew to the flawless execution of applied mathematics and electrical engineering. Inside the superfortress, the gunners operated in a state of relative comfort, wearing lightweight flight jackets, enjoying the heated pressurized air, and communicating calmly over the interphone system as they methodically destroyed the desperate waves of Japanese interceptors. They were not merely aerial gunners, they were systems operators managing the most advanced computational network ever deployed in combat up to that point in history. The contrast between the sweating, freezing, desperate Japanese pilot fighting his stalling aircraft and the American gunner calmly turning a dial to adjust the reticle size on his target perfectly encapsulated the massive industrial and technological supremacy of the United States. However, the absolute dominance of the high-altitude Central Fire Control System eventually encountered an unexpected strategic pivot. As the strategic bombing campaign against Japan progressed, the commander of the 21st Bomber Command, Major General Curtis LeMay, realized that high-altitude precision bombing using high-explosive ordnance was failing to achieve the desired destruction of the highly dispersed Japanese cottage industries. The violent high-altitude winds of the jet stream which blew the bombs miles off target, combined with the frequent dense cloud cover over the home islands, severely mitigated the offensive power of the superfortress. In a deeply controversial and brutally pragmatic decision, LeMay ordered a complete overhaul of B-29 tactics. He decided to abandon high-altitude daylight precision bombing in favor of low-altitude nighttime incendiary area bombing. To maximize the bomb load of the B-29s, LeMay ordered the removal of nearly all defensive armament. The complex General Electric central fire control systems, the heavy analog computers, the Selson motors, the Amplidine drives, and the thousands of rounds of heavy .50 caliber ammunition were physically stripped from the bombers, leaving only the automated tail turret to defend against rearward attacks. This drastic stripping of the B-29's defensive systems was predicated on the calculated risk that the Japanese night fighter forces were highly disorganized, poorly equipped with airborne radar, and generally ineffective. By attacking at 5,000 to 8,000 feet under the cover of darkness, the superfortresses could carry massive payloads of M69 incendiary cluster bombs, completely devastating the highly flammable wooden infrastructure of Japanese cities like Tokyo, Nagoya, and Osaka. This low-altitude firebombing campaign, orchestrated by LeMay, ultimately broke the back of the Japanese war economy and caused unprecedented urban destruction. Yet the eventual removal of the Central Fire Control System for these specific low-altitude nighttime missions does not diminish the sheer technological triumph the system represented. During the critical daylight high-altitude raids of late 1944 and early 1945, the General Electric system proved to be an invincible shield. It forced the Japanese air defense network into a state of terminal exhaustion, depleting their reserves of experienced pilots and revealing the complete obsolescence of manual aerial gunnery. The Central Fire Control System of the Boeing B-29 Superfortress stands as the undisputed genesis of the computerized modern battlefield. It was the moment in military history when electromechanical calculation definitively surpassed human reflex and physical intuition. The analog computers calculating windage, gravity, and parallax in the freezing skies over Tokyo laid the foundational engineering principles that would eventually evolve into the digital fire control systems of modern main battle tanks, the automated tracking radars of anti-aircraft missile batteries, and the sophisticated targeting pods of contemporary fighter jets. The Japanese interceptor pilots, fighting with immense bravery and fatalistic dedication, were not merely defeated by a better airplane. They were systematically annihilated by a mathematical equation encoded in copper wire and steel gears, solving the geometry of their destruction in real time faster than they could possibly react. It was a secret weapon of profound complexity and terrifying efficiency, a silent, invisible calculation that forever changed the mechanics of aerial warfare and demonstrated the absolute devastating power of American industrial science. As the war entered its final devastating months, the mere presence of the B-29 formations high above the Japanese mainland became a symbol of unstoppable industrial might. The Japanese civilian population, enduring the relentless air raid sirens and the horrific devastation of the incendiary campaigns, looked up into the stratosphere and saw the contrails of the massive silver bombers painting the sky, perfectly aware that their own military was powerless to stop them. The failure of the Japanese interceptors to break the defensive formations of the superfortresses was not a failure of courage or martial spirit, but a fundamental failure of technological infrastructure. The Japanese Empire, stretched to its absolute breaking point, lacked the research facilities, the rare earth metals, the precision manufacturing capabilities, and the vast electrical engineering sectors required to build anything remotely comparable to the General Electric analog computers. The central fire control system was an artifact of a society that possessed the luxury of approaching warfare as an incredibly complex engineering problem capable of diverting immense resources to solve the specific micro-challenges of aerial ballistics at 30,000 feet. The legacy of the American gunners who operated these systems is a testament to the rapid evolution of human-machine integration. These young men, many in their early 20s, were trained not just in marksmanship but in the basic operational parameters of analog computation. They learned to trust the machinery, to understand that their physical inputs were being refined and perfected by the invisible whirring gears beneath the floorboards. They experienced combat through the lens of a combining glass, watching the enemy aircraft burst into flames from the synchronized fire of turrets they were not even physically touching. The Boeing B-29 Superfortress, with its pressurized cabin and remote-controlled weapons, effectively sealed its crew inside a protective technological bubble, isolating them from the freezing hostility of the upper atmosphere and the immediate physical violence of the enemy fighters. It was a massive leap toward the detachment of modern warfare, where the operator manages the destruction of the enemy through screens, dials, and electronic interfaces, relying entirely on the absolute precision of the machines they command. The skies over the Japanese home islands served as the ultimate brutal proving ground for this concept, proving once and for all that the future of combat belonged not to the swift and the brave but to the mathematically precise and the technologically supreme.